Alright, okay, so I wanted to do a little continuation of projectile motion and do a couple examples for you here. The first we're going to start with just a simple example about the simplest projectile you can do, which is sending something off a vertical surface horizontally. So it's like off the top of a table or off a cliff, and we'll send it off this way, and then we'll watch its path as it goes down, and we'll try and figure out everything we can about it, like just from knowing how high it was initially and what its initial velocity was, right, and whatever its height is. We're going to want to essentially just figure out how far it lands away from the cliff and how fast it's going when it hits the ground, how long it's in the air, all these kind of things. So if we just make up some numbers here, let's just say this is 7 meters per second. I mean, it could really be anything. And this is going to be, let's say, a 50-meter high cliff. So how do we go about doing this? Well, as I stated in the other video, you want to break this into a vertical problem and a horizontal problem. And one of the things you should have seen in demonstration is that if we shoot something out horizontally and we drop something from the same height, that they'll both hit the ground at the same time. That vertical motion really has nothing to do with this horizontal motion. And if you haven't seen the demo for that yet, then I'm sure you can find a quick, easy one on YouTube, or it just means I haven't shown it in class yet, and I will show it. But yeah, shooting something out horizontally like this and just dropping something, just letting it go from the same height, they'll hit the ground at the same time. So that's another reason we want to just break this into a vertical problem and a horizontal problem, because for example, if we want to know how long does this take to hit the ground, well then all we really have to answer is how long would it take for something falling straight down from that height take, like how long would that take for it to hit the ground, and then we've got the same answer. So we really do want to separate these and pretend these are two totally different questions. So over here we can have an initial velocity, a final velocity, an acceleration, a displacement, which we'll call delta y. I think I wrote delta x here, so we'll make that a y, delta y, and then a time. And so we'll need to fill out everything we can there. Horizontally, now you can go through, and I'll do this the first time, but after a while I'm going to only start writing three things. You'll have an initial velocity, a final velocity, an acceleration, a horizontal displacement, which would be, this distance here, delta x, and then a time as well. So these 5 things. Now, when dealing with the horizontal part, you can just automatically, as long as there's no air resistance and it's not powered flight or something like that, you can just say the horizontal acceleration is 0, which immediately reduces these down to just v in the x direction. And it's not going to change, and everything, and so on and so forth. So now the time, or now our problem becomes just filling out the rest of these with either things we know or things we don't know. So for example, the initial velocity in the y direction, I should put little y's on these, I should have, I'm sorry I didn't, and the acceleration in the y direction, and this is in the x direction, and this is in the x direction, and this one's in the x direction. So in the y direction, our initial velocity is 0 because we're shooting this out horizontally. That means there is no vertical component, and so this is 0. The final velocity in the y direction, that's something we don't know. We'll get that at the end. When we get down here, there'll be some final velocity in the y direction. We don't know it now. The acceleration in the y direction is g. All right, that's our negative 9.8 meters per second squared. And delta y, now you may be tempted to say, all right, delta y is 50, but you have to be careful about this because we're going from 50 down to 0, right? So the actual delta y is technically negative 50 because you're going, remember, change in something is final minus initial, so it's y final, which is 0, minus the initial, which is 50, and gives you negative 50. And the time, again, is something we don't know. All right? Coming over here, we don't know the time. We don't know how long it's going to be in this flight. We haven't figured it out yet. Delta x, we also don't know. So we don't know delta x. We can't solve that. And then Vx, well, we do know Vx because it has an initial velocity that's only in the x direction. It only has this x component, which means this is 7 meters per second. And so now I want to be able to solve one of these, and then the link, if you remember, between the two will be the time. So if I look at the horizontal problem, there are 3 unknowns. Basically, we don't have to worry about that one. We don't have to worry about those two. We really just have to worry about this one and then these two. So there's 3 unknowns, and I only know one of those 3, which means I can't solve this yet. But if I come back over here, I have my 5 unknowns, and if you remember, you have to know at least 3 of them, and we know 1, 2, 3 of them. So we can start solving this vertically with our kinematic equations. So let's just start with that. We'll write them out here. We'll have delta y is equal to 1/2 gt squared, where this was a, but now it's g, it's our acceleration, plus vi t, and then the other part is v final is equal to gt plus v initial. All right, so these are what we can use. We really don't need any more than these, but we may or may not use another one. So first things first, this VIY, this is 0, which makes this 0 and this 0, because those are both VI in the y direction. Still forgetting to put those subscripts on them. Sorry about that. And this is VFY. Okay, so this is 0, which really reduces this down a little bit. And if I look at this version here, well, I know delta y, I know g. The only thing I don't know is t. All right, so I can use this to solve for time. And if I isolate time, I'll let you practice that math, but you should get 2 delta y over g and then square rooted. Remember, something to the 1/2 power is the same thing as square rooting it. All right, so that gives us this answer here, and that gives us what the time is, which means we could now go in and plug in values for this. You could plug in -50 here, 9.8 here. You'd get, all this and take the square root, or not 9.8, but -9.8. So we end up with, this is about 100 over 10. So you end up with the square root of 10. And so you're getting around 3 seconds there. It should be around that kind of 3 seconds, assuming I didn't make any mistakes there. And now that I have this time, I could come over here and use that and solve this part, but I'm going to start right here. I'm going to go ahead and find this final velocity. And so the final velocity in y is g times t, but we just figured out that t is 2 delta y over g, and it's square rooted. Okay? And from there, this would allow us to solve all of these. So if I wanted the actual time, I could just plug my numbers in that I had right there, and I would get the time. And if I want v final in the y direction, I just plug my numbers in there, and I will have my answer. But I don't like to do that until I get to the very end. I prefer to just kind of go with this. And actually, I can reduce this one more because I have this g here, and so I have a g over a square root of g, which really just makes this the square root of 2g delta y. So now you have g over square root of g. That just leaves you with square root of g, which means I can just put it under the same square root as these other ones. So 2g delta x, and it's all square rooted. Square root of 2g delta y. Oops, I said x. Delta y. Okay? And so that would be my vertical stuff, and I would have this whole side done. And then that means I could move over here. I can go ahead and say that this equals that square root of 2 delta y over g to the 1/2. And now I could solve this side, because I know that velocity in the x direction is equal to displacement over time, which means this is just displacement, whatever it happens to be. We can solve for it, and we get that displacement equals final velocity, or velocity in the x direction, which would be our final velocity, times time, in which case delta x then equals our velocity. We could plug that in. It would be the 7, and then times this 2 delta y over g. And so essentially at this point, I've solved all of my unknowns. The only thing I haven't done is actually plug my numbers in from up here into these equations and gotten these. I'm going to leave that for you to do because it's essentially just plugging numbers into a calculator. It's nothing real hard. You put, again, you put 2 here, you put negative 50 here, you put negative 9.8 here, and you type it in your calculator, take the square root, you're done. Here you put 2, negative 9.8, negative 50, square root it. Here you put 7, negative 50, negative 9.8, take the square root, you're done. And in fact, you wouldn't even do that here again because you would have already found it right here, and you would just use that. To do it. Now, that would be pretty much that example. The only thing really left you could do is you could take this final velocity that you would get here, this VFY, and I'll do this in another color. So if you wanted to know what the actual total final speed was, and you could say, all right, here is Vx when it hits the ground, like how fast that is going, and then add on to it, perpendicular to each other, VFY. And that would just be Pythagorean theorem, and you could use that to get the actual final velocity that it hit the ground with, just VF. And so you could say that velocity final that it hits the ground with squared is equal to V in the x direction squared, which is the 7, plus VF in the y direction where it hits the ground, this that you would find right here, squared. And then you could just solve this, take the square root of both sides, plug those values in you found, and then you'd be done. You would have just about everything that you could find with this, and it would be completely solved. All right. This video is getting a little long. I think I'll change mine. I'll go ahead and put another example in a separate video just to kind of break it up a little bit. But in the next one, we'll do one that's starting from the ground and going up over and to the ground. And it's a little more complicated than this, but it's not too much more complicated. It's really just filling that part out is a little more complicated, but after that, it's just algebra again. All right, that's all for now.